Hello, everyone, and welcome again to the next seminar of the AnalytiXIN Manufacturing Data Assets Research Project. Today's seminar is being held by University of Notre Dame, and I am passing on the baton to Jahanju, who will start talking about the 3D printers and the insights that they have generated from working with.
Hello, everyone. My name is Jahanju from University of Notre Dame. Today, I'm going to talk about our recent work on the Notre Dame Engineering Innovation Hub and Engine Science. My work is mainly about 3D printers. At Engineering Innovation Hub at Notre Dame, there is a room for 3D printers. There are a bunch of 3D printers in that room, and there's a main electrical panel. In that panel, we installed a device named the MVP kit. That kit can record the energy and power related information and send this information to the AWS cloud. Basically, this process is done by ignition. The ignition frequency is typically 1 second, which means we can get energy and power related data every 1 second. And it is a continued process, and it will be updated every 1 second. All of the data, including the historical data, are stored in the AWS S3 bucket. Apart from the AWS cloud, we have another platform to visualize the data. We are using the Mega AI platform for visualization. The Mega AI platform can directly pull the data from the AWS cloud and generate some graphs for us to gain insight into the data. This can right now, these kind of data are related to the energy and power information. A part of this kind of data, we have another kind of data, which is from the printer logs. Okay, the 3D printers at EIH are managed by a platform named GrabCAD. So students can submit their printing job through the from their end of the GrabCAD, and the administrator at EIH can view the job and assign different printers for different jobs. So all of the printer log information are recorded on the GrabCAD side. And there's a local computer which we can download the data from GrabCAD. Okay, so right now we have two kinds of data. One is for the energy and the power related data. The other is related to the printer log. Now let's take a look at the data. Okay. For the data on the AWS cloud, these data are related to energy and power. For example, the true power, the apparent power, and also voltage and current. And then we can use the Mega AI platform to visualize the data to see how each property change over time. For example, I showed the total true power here. This is basically how it looks like. Also, for the printer logs, we have the job name, the start time, the complete time, also the status of the printers. These are all about the printer information. So now we have the printer logs, we have the data from the AWS cloud. Then we were thinking about using this kind of this kind of information could train a neural network which can predict the printer status. Okay, so we want to know how many printers are operating given the power and energy related information. To do this, we need to do something with the data. We cannot directly use the data. We need to do some data pre-processing. For example, we need to deal with the missing data and also the repeated measurements. For the missing data, this issue comes from the very early stage setup. It's only it happens at the very early stage of the project. Now we rarely see the missing data. So for the missing data, we just use the interpolation, which means we take the average value of the neighboring cells of the neighboring data. For the repeated measurements, we, for example, at the same timestamp, there may be 3 or 4 measurements. However, as I mentioned before, the ignition frequency is 1 second, which means we are supposed to have 1 measurement at each second. Sometimes there can be multiple measurements. They are at the same timestamp, but they are at different nanoseconds. This is also due to a very early stage setup issue. So in order to have a clean data set which has property recorded at each second, we need to eliminate the extra values. So we only pick the maximum value at each second. Apart from the missing value and repeated measurements, we need to apply a moving average filter to smooth the data. As we have seen before, the data has a lot of fluctuations. Although the ignition frequency is as small as 1 second, we can still see some fluctuation. So we need to apply a moving average filter to smooth the data. And also, in the 3D printing room, there are 3D printers, but there are some other electronic components, for example, the lights, the TV, and also there are some support removers. So that means the power and energy related information is not only for the 3D printers, but also for the TV and some other components. So in order to predict the printer related information, we need to remove the background noise, which means we need to remove the effects from the TV and other electronic components. The processed data set will be something like this. The first column is timestamp. The second column to the fourth column are about the energy and power related information. For example, this is total true power, total apparent power, and voltage, current. And the rest columns are printer status. 0 represents off, and 1 represents on. Using this data set, we can build a model to train and do some prediction. Also, after that, we do some model assessment. For the data set, this graph shows how it evolves with time. The blue line is the original signal, which is the total true power. I remove the background noise and I can get the yellow curve. Also for the red curve, this is the printer status, which shows how many printers are operating and we can see they did related to each other. And for the results, I used the random forest classifier to perform the job. Well, firstly, I use only 4 predictors, which are the total true power, total apparent power, current, and voltage as the predictors. The accuracy is only about 7 to 8%. Then I added another 2 features to predictors, which are the day of the week and also the hour of day. And the accuracy can be increased to nearly 98%. And we can also see, for example, we can see from here, for example, when the true label is 1, okay, the predictable, there are over 6,000 cases where the predicted label is 0. However, if I added these 2 features, okay, there are only 600 instances where the predicted label is 0. So we can see there's a significant improvement. And I also plot the feature importance, which we can see the day of week and hour of day. They did play a large role in the decision-making process. Okay, apart from predicting printer status, we also did a real-time forecasting. For the real-time forecasting, let's first talk about the ARIMA model. Okay, ARIMA is autoregressive integrated moving average. Okay, the first part, autoregressive, means the current value depends on the previous value. And there's a parameter to help you understand this part. A parameter P is actually the represents how many previous values we use in the ARIMA model. Okay, a higher value of P means we use more terms, we use more previous terms, and which means which implies a more complex autoregressive relationship. And for the moving average part, moving average means the current deviation depends on the previous deviation. And also we have another parameter Q to indicate how many previous deviations we use in the model. Okay, now we have AR and MA. We still don't know I. What is I? I is the integrated, which means I need to mention that before. It's like for the ARIMA model, we need to use the stationary data set. Okay, if the data set is non-stationary, we need to make it stationary by doing differencing. The integrated means differencing. So if the data set is already stationary, then we don't need to do differencing, which means D is 0. Okay, if we can make the data set stationary by doing differencing only once, then D is 1. For example, if for an ARIMA model, 2, 0, and 1 means the current value depends on 2 previous value. Okay, this is 2, and we only have 1 error term. This is 1, and we do not do any differencing, so this is 0. Okay, so for ARIMA model, selecting the P, D, and Q values is very important. I did a research to find the optimal P, D, and Q values. For example, if I want to do a power prediction, I want to do the real-time power forecasting. The 0, 1, 2 combination is the best. If I want to predict energy, because energy has a different pattern, the 1, 1, 1 combination is the best. And after doing the research, I use the best combination to perform the prediction. Here, I train the ARIMA model on the March 7th data. I use the whole day data to train the model. Then I can use the ARIMA model to forecast the energy consumption after that day. Okay, the prediction is made every 5 minutes. Then I give the actual data after 5 minutes to the model, and the model can be retrained and make new predictions. So the model can see the new data every 5 minutes and give predictions every 5 minutes. The root mean squared error is only 0.56, which is quite small compared to the average value of the energy consumption. The accuracy is pretty high because the energy curve is very smooth. Then how about power? Because power data has a different pattern. It has more fluctuations than the energy curve. For the power curve, the root mean squared error is more than 200, but still, compared to the average value, still this model is accurate enough. Okay, so to sum up, our model can do a printer status prediction. Okay, we can use the energy and power related information to inform the printer status. And also we used the ARIMA model to do the real-time power and energy prediction, which is quite accurate. Then by doing all kinds of these techniques, we can help the organizations to making informed decision on real-time insights, and this can help to enhance the operational efficiency, and also can lay ground for future innovations. And that's the end of my presentation. I'm happy to take any questions.
Does anyone have any questions, or should we move on to the house mail?
I do have one quick question. So in the prediction model, you are using past values of power to predict future values, right?
You mean the ARIMA model?
Yes, yes.
Yeah.
So my question is it just univariate analysis, or can you also use multiple variables, for example, temperature or other stuff like that?
You mean use other parameter, using other properties to help me to
Yes.
gain more accurate result on the energy and power forecasting?
Yes, yes.
Yeah, that's a very good idea. Yeah, using other properties can help improve the accuracy. But right now, I think the accuracy is already fine. For example, the accuracy is over 99%. And for the power, although it has a lot of fluctuations, the accuracy is already over 90%. So yeah, using other properties can help. That can also increase the computation burden. So
do you know if
right?
ARIMA model can can actually take other properties, or is it just univariate analysis method?
I don't know if ARIMA model can actually take other properties, but for other models, I do think they can use it. Yeah, but for ARIMA model, I don't think so.
Okay, thank you.
Any other questions?
If there are no more questions, we're at almost the half point, so we can just move on to the Haas mill.
Okay. Let me share the screen. Okay, so can you guys see my screen?
Yes, we can see everything.
Okay, great. Okay, so yeah, hello everyone. My name is Xinyan Liu. I'm a fourth-year PhD student from the Department of Aerospace and Mechanical Engineering. So today I will present our recent work about the energy and manufacturing data analysis, which is based on the data collected during the drilling experiment using the Haas mill. Okay, so first some background about the machine we use. So the machine is called the Haas TM1P, and which is a 3-axis CNC machine. So here's some basic parameters for this machine. The spindle speed, the maximum spindle speed is like 6,000 RPM, and with a maximum power about 7.5 horsepower. And here's axis travel, 30 inches in the X direction, 16 inches in the Y direction, and 16 inches Z direction as well. And about the data collection, we use similar devices as Jahan just introduced. We collect the energy data every second, which includes the true power consumption, apparent power, power factor, and many more. And about the manufacturing data, we also collect the spindle speed and the machine status, like the whether emergency error come up or something. So yeah, those are the backgrounds for the machines. And then we design an experiment to investigate the influence of different parameters in the drilling process on energy consumption and the drilling quality. So we choose 4 parameters that we think may have like significant influence on the energy consumption and drilling quality. They are the spindle speed, feed rate, material type, and the drilling approach. So in the experiment, we drill like 180 holes in total on 6 material bars, including 4 aluminum bars and 2 low carbon steel bars. And to be more specific, we drill like 30 through holes on each of the bar. The distribution of the holes is shown here. So, and the diameter of each hole is like 1/2 inch. Okay. So about the drilling approaches, we designed 3 different drilling approaches. So the first one is more like a conventional drilling approach, which uses drill bits, and it's called the pack drilling. So in the pack drilling, we actually derived like 2 kind of sub approaches with different pack depths. Okay, so in the pack drilling, the drill bit will first go down for 1 pack depth, and then it will just go up and pause for a while for cooling, and then just go down again, go deeper. Okay, this is the first 2 approaches, the pack drilling. And the third one is called the end mill continuous with a ramp spiral. So in this case, we do not use drill bits. Instead, we use end mill. The end mill has a slightly smaller diameter than the desired hole size. So we need to do a spiral, and so that means we are doing a circle simultaneously as we are going down. We go deeper. And the last one is called the end mill discrete method, which we decouple the circle movement and the downward movement, which also use the end mill. Okay, so yeah, those are the parameters we use when we're doing the experiment. So the first table shows the parameter we use during the pack drilling. We draw on both aluminum and steel bars in the pack drilling. So we choose the spindle speed to ranging from 1,000 to 1,500, and varying the spindle speed every 100 RPM. And the packing depth for aluminum, we choose a slightly aggressive packing depth, which is 0.1 and 0.2 inches. And for steel, we choose a slightly smaller packing depth because, the steel are more stiff, so we need to be more cautious about this. And for the feed rates, they ranging from 5 to 25 inches per minute. Okay, and then about the end mill drilling, we only test on the aluminum because it's not the conventional way to drill a hole, and it will make it more difficult to drill on steel. So we just test this on aluminum. And the spindle speed is significantly higher, ranging from 4,000 to 4,500. Okay, so these are the data we collected during the experiment. This figure shows the energy consumption data when we're doing the experiment about using drill bits, or you can see the pack drilling method. So the left box shows the energy consumption history data when we draw on aluminum. And the left side shows packing depth with Q equal to 0.1 inch. And the right side shows packing depth equal to 0.25 inches. So you can clearly say that when we are doing larger packing depths, the power consumption goes higher, but the drilling time it consumed becomes shorter. And then about the steel, of course, we are using the even more smaller packing depths, so the total time consumed is much more than we draw on aluminum. And also, as a last time step, you can see there's abnormally high energy consumption, which is actually a normal situation when the materials stick to the drill bits and we have to emergently stop this machine. So you will see a very high peak and then we stop it. Okay, so if we this just shows the energy consumption history when we're doing the end mill drilling. So compared to the previous one when we do the pack drilling, end mill drilling actually takes much longer time. And you can see lots of those peak values. This is because when we're doing the end mill drilling, the end mill becomes overheats very frequently, so we have to stop and restart it. So those peaks are due to those restarting process. When we compare the continuous drilling and the discrete drilling, we can see that for this discrete drilling, we saw lots of fluctuations because it decouples the downward movement and the cycling movement. So when you go down, you will see a small peak there. Okay, so if we zoom in the energy consumption history about of using the drill bits, which is a packing drill method. So you can see in one origin box, this is the energy consumption while we're drilling a single hole. So this number shows spindle speed. So as you can see, as we like increasing the spindle speed, the energy consumption goes up, which is consistent in all the feed rate. And also, if you're comparing different feed rate, you will also observe a higher energy consumption. And from another aspect, you can see that the spindle speed has nearly zero effect on the drilling time. So they are almost drill the hole at the same speed, but feed rate has significant influence on the drilling time it consumed. Okay, then here's data that we collected, we processed to train a deep learning model. So the spindle speed as the setting spindle speed, not the actual spindle speed that we measured. Then the feed, which is the same case for the feed rate, which is the setting feed rate. And then the materials are represented by a binary value, which one extent represents aluminum and two represents steel. For the drilling approaches, we also use 4 integer numbers to represent different approaches. So when we're training the deep learning model, for the spindle speed, we use regression, which is the same case as feed rate. And for the materials and drilling approaches, since they are discretized values, so we have to use classification. So that means for these two variables, we use cross entropy loss, and for the two regression value tasks, we use MSE, mean square error. And after we remove those abnormal values, we got 171 clean samples. So we feed this 171 samples to train a deep learning model. So one of the model we used is called the transformer, which is the backbone of almost every advanced large language models we use nowadays, like GPT or something. So here we use a transformer model with encoder only structure to handle this time series data. So that means what we take in is the energy consumption data. And for some cases, we also have the spindle speed. So the input data are these two, true power, the power consumption and the spindle speed. And then we add a positional encoding, which is actually a linear positional encoding. And then the encoded information is inputted to multi-head attention, which is a core part of this transformer structure. And we use 4 layers of this multi-head attention there. So the output is generated by a linear layer, and the output is divided into 2 parts. One is for the regression task, which outputs a feed rate, and in some cases we also output the predicted spindle speed. And another one is for the classification tasks, which we output the operation type and the material type. So those are discretized value. And to make this model more concise, we just use one neural network to give prediction for 4 variables, such as feed rates, operation type, material type, and spindle speed. And Yeah, so let's move on to see the results. So this table shows the training error. So we also compare the transformer results with LSTM, which is short for long short-term memory. So you can see in the variable that we care most, which is the drilling approaches, transformer get much higher accuracy, which achieves like 81%. And for the feed rates, LSTM is slightly better, but but on the spindle speed, the transformer gets us slightly better. So in the later afterwards slides, I just show the transformer results. So if we only use the energy data, which is obviously more convenient to get than the manufacturing data, because not every machine is computer controlled. So for those more traditional machines, it's very hard to get those spindle speeds in real time. But almost every machine uses electricity, so it's much easier and generalizable to train your model based on the energy data only. In this case, then the cross mark represents the predicted value, and the blue dots shows the label data, the experiment data we collected. Okay, so you can see the transformer model had a difficulty in predicting the spindle speed, because they are like varying a lot from 1,000 to 4,500, and they are like clustering into small regions. But for the material type, the transformer has achieved like 100% accuracy. So also for the operation type, you can see so 1 and 2 represents the two packing drilling approach. They can like 100%, it achieve a 100% accuracy. But for those animals, it turns out to be much more difficult to predict. But since our machine is a CNC machine, so we actually have access to the spindle speed. So if we adding the spindle speed as the input data as well, so the performance will improve a little bit, but it's significantly improved for the feed rate. Of course, it's highly related to the spindle speed. So once you provide the spindle speed, the feed rate accuracy can be significantly improved. So this figure is just to compare the two prediction results. Once the left side shows without any spindle speed data, and the right side shows feed rate predicted with the spindle speed data. So you can see with the spindle speed data, the predicted value are more like gathering around this label data. Okay, so about the future directions, we also measured the quality of this drilled holes. So this figure shows raw data that we measured. We use a laser-based device to measure the depth of each of the hole. So the color shows the z direction coordinate of this drilled hole. And after some data process, we got the boundaries of this hole, and then we visualize the radius of this drilled hole. So the x-axis shows the rates, and the y-axis shows the radius at each angle. Okay, but here you can see the data contains lots of noise. So the next step is to improve the measurement process to like reduce the noise, and we will use a higher resolution to help alleviate this issue. And after we get a clean data for the whole quality, we plan to combine the prediction model with this quality data to optimize the drilling process to like make it use less energy and achieve higher quality. And also, we will perform extra experiment to adding more data to train the prediction model. And last one is maybe we can use reinforcement learning techniques to optimize the drilling operation in real time. Okay, yeah, that's all. Thank you. I'm happy to take any questions.
Any questions?
I have a question, but I'm not sure it's to AI. It's to the measurement of the accuracy of the radius of the hole. Can you go for a second to that graph? It looks
you
like
mean this one?
Yeah. It looks like it has 2 pi periodicity on the envelope, which looks like a sinus. So, right, you kind of see a maximum exactly in the middle. And the envelope that goes as a harmonic function to the sides.
Yeah.
Which means to me that you have a distortion in the measurement, which your whole circle is basically squeezed in one direction.
Yeah.
And it cannot be due to the drill, because the drill will make a perfectly round hole. So you do have some imperfection. You have a systematic error in the way you measure that.
Yeah, but we're not sure if it's because of the measurement introduced the system error or it's introduced by the drilling process. So, yeah.
What
do you say is right?
Cannot result in an elliptical hole. It will have exactly round hole. You know, the fact that you have an envelope that looks like a sinus means that you measure ellipse. Otherwise, you would be measuring an exactly straight line.
Okay, yeah, maybe, but not sure. But about the drilling, even if we use the drill bits, we can still have those distortions, right?
You still can have an elliptical hole.
Yeah, I'm not very familiar with this manufacturing. Since I'm more like a deep learning guy, but I'm not sure. But we will sure investigate that. Yeah, thanks for your advice.
What is the axis dimension? Is it in millimeters?
In millimeters. Right.
So you have here about 200 micron tolerance, right?
Yeah.
Okay.
So one thing I can say that I think the measurement device we need to do a better job with that. I think if you look at some of this stuff, you could see some systematic errors in terms of the measurement. You could have a little bit of wobble in the drill bit, and so what would be interesting is we need to label the axes with the units and everything. I guess this is like radians on the x-axis, but we should see Shenyang, which direction is it, and all the holes going that way. So maybe the structures are stiffer in the y direction than the x direction, for example. You might get a little bit, just a slight bit of wobble. It's really not that much. I think it's mostly those big spikes you see are artifacts of the optical measurement technique. We need to do.
They look almost periodic, which is kind of like surprising, right? If that is a fabrication artifact, that would be very surprising.
I don't think it's an artifact of the drilling. You might see some you know, a little, I don't know, on, you know, a little edge from one side or something, but that's an artifact, I think, of the measurement device. We need to do a better job with the optical measurements.
Interesting. Okay. But it's impressive that you have all those tools. That's very impressive.
Yeah.
Any other questions? All right, well, if there are no more questions, thanks again to the Notre Dame team for the presentation, and we will post the recording on our YouTube channel as usual, and we'll see you next month for the Indiana University seminar. Thanks a lot.